Hello folks, and welcome to this video session on deconvolution. But before we talk about deconvolution, let's do a quick recap on the previous well-test session on the theory and practice. So we had a look at different well-test analysis tools, and including the data plot, showing the pressure and the rate versus time. With different PBU tests here. So for a particular PBU test, we could plot the superposition plot, showing the pressure versus superposition time. And in that particular case, for gas condensate well, we use pseudo pressure, MP, and that was to try to linearize the flowing equation. And as well, for a particular PBU, we could plot the log-log plot, or also called derivative plot. And this is showing the delta P plot. So with this pressure signal, pressure at T minus pressure at shut-in, and its derivative with respect to the superposition time. And this is called the conventional derivative. And we plot these two versus the shut-in duration delta T. These are log-log scales as well. Probably that's why we call them log-log plot. We could plot the different PBUs on the same derivative plot, okay, as we did here. And that's going to give you what we call the derivative overlay. We do that to try to get some confidence in the data. It's also easier to spot the different flow regimes and to spot any dynamic changes as well. We could use the straight line analysis, so a series of straight lines to have a look at the different slope and define the flow regimes. And we could push the analysis further with the type curve simulation. So far we use the derivative plot and the conventional derivative to drive the analysis. Then we have a look at the superposition and the data plots as verification tools. The superposition plot is going to help you with initial pressure. And as for the data plot, you need to make sure that the PBUs are matched. If they are not, that means that your permeability or your initial pressure are not correct, or that you need to add or remove some boundaries in your model, or add or remove some changes in reservoir properties in your model as well. Sometimes you cannot expect to match all the PBUs with a simple analytical model. And for example, that could be because of changes in the fluid density below the gauges, or it could be due to a multi-phase region evolving away from the well and changing your total compressibility. If the PBUs are not matched, we need to understand the reason. Once you're happy with the PBU test, then we can have a look at the production periods. And this is going to give you some information about the skin and the evolution of the skin over time and the turbulence factor as well. So deconvolution is the fourth tool in the well testing toolkit, and it's a very powerful one. So don't get fooled by this complex name, deconvolution. You're going to see that the technique and practical use of deconvolution is not that complex. So we're going to see the definition, what is deconvolution. We're going to see the benefits of using this tool and the limitations. Okay, so let's imagine a well with this pressure and rate data. So we've got production startup here with the first flow, the first PBU, pressure increasing this way, flow after flow test, and a main flow here, and the second PBU, like this. So here on this log-log plot, I've plotted the response from, let's say, this PBU, which lasts 100 hours, as you can see on the log scale. So in a linear system, we should have the superposition principle, and which is characterized by this equation. Okay, so initial pressure minus the one flowing pressure at T is equal to integral of 0 to T of the rate times the derivative of this function PU with respect of time. What is PU? Well, this is the pressure response to constant unit rate production period. So I'm going to repeat that. So PU is the pressure response to constant unit rate production period. So if you like, PU is the equivalent initial drawdown, as we saw on the previous session called well testing theory and practice. So PU is the equivalent initial drawdown response, if you like. So the deconvolution algorithm is going to extract PU based on these different inputs. So we're going to input an estimate of initial pressure. We've got our wall pressure here from this PBU, and we've got the rate here from the rate history. Now deconvolution is going to extract PU, and this is the response here in red. So from initial pressure, then we've got this pressure that decreases. So this is the equivalent constant rate production response. Some well-test program, in fact, doesn't show you the constant unit rate production response, but it's going to multiply it by the rate before the PBU. So this is, if you like, the equivalent initial drawdown. We've got only one single production period, and we've got pressure decreasing this way. We can plot this response into the log plot. So now for delta P, we can use this pressure signal, initial pressure minus pressure at T. Then we can use the derivative of this delta P, or pressure, with respect to the log of time. We don't need to use the superposition time. This is the initial drawdown response. We've got only one rate period here. So we don't need to use the superposition time. We can use the log of time. So if we do that, this is the response that we get in red here. And this is deconvolution. So when we look at this plot, we can see two main differences between the conventional and deconvolved response. The first one is that deconvolution lasts longer. Okay? This is because we derive the deconvolved response from 0 to T, from production startup to the PBU of interest. So we derive deconvolution over the entire test sequence from 0 to 300 hours. So now we've got a response that lasts 300 hours. Okay? As for the blue, or the conventional response, this is dictated by the shut-in duration. In this particular case, we've got only 100 hours here. So the deconvolved response is derived over a longer time interval. In fact, of duration equal to the entire test sequence. So now we see further away in the reservoir. Deconvolution adds some reservoir insight. So we might see an horizontal radial flow regime, or we might see the presence of boundaries. While for the conventional response, this is only dictated by the shut-in duration. The second main difference between conventional and deconvolved response here, if we look closer to this plot, the two are not exactly the same, okay? And this is because of the way we derive or we define these two derivatives. As we mentioned, for the deconvolved derivative, we are using the log of time. This is where well-testing theory applies. This is the initial drawdown. We don't need to use the superposition time. We can derive delta P with respect to the log of time. As for the conventional response, the blue response now, we derive the pressure with respect to the superposition time. And if you remember with the previous session, this is quite a monstrous equation, complex time function, and it has some assumptions. And one of them is that we reach radial flow regime. And that means that we might have some errors when we derive this conventional derivative in blue. Okay, we might have some errors, and these are called commonly distortions. In fact, if you look at the blue response, it looks a bit delayed compared to the deconvolved response. And this is sort of basic distortion or basic error. We might see a lot of distortion, for example, if this flow period before the PBU doesn't end during radial flow regime. So when you look at deconvolution, what you get now is a sort of pure signal. It's free of any distortions. All the things that we learn about well-testing theory, the different slopes, the straight lines, etc., that will apply to the deconvolution. If you like, it's a sort of improved derivative. It's free from errors and free from any distortion. So now we should use the deconvolution response to drive the analysis.